Today we want to continue looking at our next big thing, which is finding the area under a curve and above an interval on the x-axis. The big idea here is that we want to calculate area as length times width, because all we ever do to calculate area is length times width. All we're ever doing is calculating area as length times width. We just have a couple of pre-worked out versions of length times width. Length times width is what we use for rectangles, because that's the easiest one. The length is always the same. For triangles, we say 1/2 base times height, because we've already worked out that the triangle is half of a rectangle. We've already worked out what happens to that with that variable length when it's a line. We make triangles. We already know that the area of a trapezoid is the average of the bases times the height. So we pre-worked out a lot of areas that we carry around with us. But we want to understand the concept more generally. And that all goes back to length times width equals area. The calculus portion of the problem comes in the fact that the length is going to be not just different, a variable, but unpredictably, continuously variable. That's the big thing. The length is now continuously variable. It was when we did a triangle, but it was very simple when we did a triangle. It just makes a line. Life was easy. We taught that to little children, 1/2 base times height, and we always remember it. Pi r squared, we remember that one, although getting to that through calculus is very messy. But all we're doing is length times width, where our function is the length, and then the delta x is some small piece of the interval to be the width. So we're just dividing the interval up into all these little sub-intervals with a width of delta x. Then we decided if we use more, so here we take care of the continuously variable part by just going with variable. We just have a bunch of variable values for the height or for the length that we multiply by the width, make things constant, so we get to use multiplication, and then we just add up all the results. And that produced a Riemann sum when we say, let's let the number of rectangles go to infinity. The important thing is when we go from the Riemann sum to the definite integral. That's the important thing to notice. That gets us to the definite integral. So the Riemann sum without the limit is a discrete model of what's going on. Limit as n goes to infinity using infinite number of infinitely thin rectangles. And our discrete sum becomes a continuous sum. Let's call it a discrete model for the definite integral, which is our continuous sum. This gives us new notation for the difference in our thinking, but it doesn't give us any kind of actionable plan. That's when we need to bring in the first part of the fundamental theorem of calculus, which we abbreviate FTC. And specifically, this is part 1. Part 1 of the fundamental theorem of calculus tells us that we can calculate a definite integral using an antiderivative. So part 1 of the fundamental theorem of calculus tells us that we can use a definite integral we can calculate I'm going to write it in the order that we normally write it. We can calculate a definite integral using an antiderivative. That's the first part of the fundamental theorem of calculus. We can calculate a definite integral using an antiderivative. Part two is just the other direction. Part two says that we can construct an antiderivative using the definite integral. Antiderivative is exactly what it sounds like. An antiderivative is a derivative going the other direction. It's asking, what is this the derivative of? This is what we want to get into today. This is our mechanics phase of what's going on. We've talked about the thinking phase. I've mentioned the thinking phase all 3 days. Tomorrow, I will not be mentioning the thinking phase because we're doing the practice test, so I won't be talking at all. Everybody look forward to that. Oh man, a whole math class where Leach just shuts up. It's all quiet and everything. But then guess what I mentioned on Friday? That's right, the thinking phase. Because stuff doesn't get stuck in your head because you hear once. Stuff gets stuck in your head because you hear it so much you can't get it out of your head. Incidentally, this is what the top part of our notes are going to look like on Friday. If you want to just get your notes ready for Friday, there it is right there. I'm just going to write this again. So, but we've already written it. We don't get stuff stuck in our heads because we've written them once. We have to write them incessantly. This is the part where I lean into the fact that a lot of you have been trained to take notes by just writing down everything I write. It's like, oh, if he writes it down, I write it down. That's how this works. So the things that we need to know about the thinking. What's the thinking about the problem that we're trying to work with? What are the mechanics that we need to learn to work those problems? And the reasons why. What are the applications of this particular problem? We've talked about the thinking phase. The problem is that we're trying to calculate area as length times width, but the stupid length is all continuously variable and shit. So that got us to the definite integral and the fundamental theorem of calculus. So that got us to antiderivatives. That's what we need to work on now, some mechanics. Antiderivative is the mechanics of the problem. I call them questions. So mechanics of the area question. So the antiderivative is going to be the mechanics of the area question. And we're going to do like we did with derivatives. We're going to take each derivative and turn it into an indefinite integral or an antiderivative. And we're going to start with our favorites. So if you would recall, The derivative of x to the n is nx to the n minus 1. If we can write powers of x, we multiply by the exponent, we subtract 1 from the exponent. What we want to do is the inverse of this. We want to invert this process of multiply by exponent, subtract 1 from exponent. That's what we do when we take a derivative. First, we multiply by exponents. And second, we subtract 1 from exponents. That is how we find a derivative. The antiderivative, we just want to invert this process. For the antiderivative, we're just going to invert this process. Everybody can make me scroll. You all have mind control powers. Like in the front row, they're not aware of the mind control powers that the back half of the class has on me. You can make me scroll by just kind of like doing one of these things. The big question is, how far can you make me scroll? If you just like keep going like this, even if there's like space at the bottom, can you make me push this all the way up to the top? Can you force me to just use this portion of the screen? That's the big question. I've heard tell of a psychology class that learned that they could control where their professor stands. So I'm kind of tied because I write down here. But what a class did was they made sure that they were evenly distributed throughout the room. And when the professor was standing on this side of the room, is this stage right? Then the class like acted all disengaged and like kind of like looked bored. They actively looked bored. Maybe they actually were. Like, you guys do a great job of it because you probably are. But anyway, they acted like bored and disengaged and they weren't paying attention. But when he walked over to the other side of the room, all of a sudden they would brighten up. Sometimes they were faking it, right? So for the most part, professors would take it. Right? They'd be like, oh wow, they're right nose, and they like nod and like smile and look happy. And what they did was they psychologically manipulated the professor only standing on one side of the room. Anyway, what are we talking about? Oh, that's right, scrolling. So the antiderivative is going to be the mechanics of this area question. We're going to take our derivative rules and turn them into antiderivative rules just by reading them backwards. Our derivative rules become antiderivative rules by reading them backwards. So our first one was the derivative of x to the n is nx to the n minus 1. The description of that is multiply by the exponent, then divide by, then subtract 1 from the exponent. Thinking of the next thing already. So if we invert this process, the first thing that we're going to do is the inverse of subtracting 1 from the exponent. We're going to add 1 to the exponent. And then we're going to divide by the new exponent. That's the inverse of this process. Add 1 to the exponent, then divide by that new exponent. And this is how we will antiderivative, integral dx. So if we integrate nx to the n minus 1, we should get back to x to the n. So what this would look like is that the integral of nx to the n minus 1 dx. The integral and the dx is part of the notation. You can't write integral without the dx at the end, at least for now. You can't write integral without a dx at the end. You don't want to write a dx without an integral at the beginning. It's just math punctuation. So the instructions for the integral thing are to add 1 to the exponent. So I get x to the n minus 1. So we add 1 to the exponent plus 1. And then we divide by the new exponent. N minus 1 plus 1 is just n. And we had an n at the beginning. N minus 1 plus 1 is n. And then the n's cancel, so we just get x to the n like we expected. The other thing that we want to remember is we're saying, what is nx to the n minus 1 the derivative of? It's the derivative of x to the n plus some stuff we don't know, plus some constant of integration. So we just put plus c. So don't want to forget to add a plus c because the derivative of that constant is equal to 0. Add 1 to the exponent, divide by the new exponent. Now this is what it looks like if we just directly turn around nx to the n minus 1 back into x to the n. In general, what we'll write is the integral of x to the n dx. We'll add 1 to the exponents and divide by the new exponents. We can write that as 1 over n plus 1, x to the n plus 1. Or some of you will prefer to write x to the n plus 1, add 1 to the exponent, and divide by the new exponents. This is the one we saw yesterday. The integral of 2x is x squared. Plus c. We're reading 2x as 2x to the first power. This is like a 2x to the 1. So when we add 1 to the exponents, we get 2. If we take the 2x and subtract 5 from it, if we take the 2x and we subtract 5 from it, we have 2 terms. When we take derivatives a term at a time. So when we do antiderivatives, we also do antiderivatives a term at a time. So the integral of the 2x part is x squared. The negative 5 we're going to read as minus 5x to the 0. So when we add 1 to the exponents, we get minus 5x to the 1. And then we divide by the new exponent of 1. Just leaves it minus 5. And then we put plus c. The antiderivatives that we write with the plus c are called the general antiderivative. So the general antiderivative is the one with plus c. I might also refer to this as the indefinite integral. More terms, more add 1, divide. Add 1 to the exponents, divide by the new exponents. The antiderivative of 5x squared, we add 1 to the exponent and get x cubed. And then we divide by the new exponents. Add 1 to the exponent, 3x to the first becomes 3x squared, and we divide by the new exponents. Four x to the 0 becomes 4x to the 1, which we don't write, and then we divide by the new exponent. We don't write dividing by 1. And then for the general antiderivative, we write plus c. Derivative drops down 1 degree, integral goes up 1 degree. The antiderivative question says, what is 5x squared minus 3x plus 4 the derivative of? We get a lot of use out of nx to the n minus 1 or x to the n plus 1 over n plus 1. As long as we can read our powers of x. The square root of x we're going to read as an x to the 1/2 power. Rewriting this as 1/2 power is not doing any calculus stuff. That's just doing algebra stuff. That's just us reading what this is. So I'm still doing an integral of x to the 1/2 power dx. That's just rewriting the radical as a fraction exponent. That's just the algebra thing. We didn't do any calculus yet. Now we're going to do calculus. We're going to add 1 to the exponents and divide by the new exponent. One half plus 1 is 3/2. And then we divide by the new exponents. It's at this point when we add, after we add one to the exponent, divide by the new exponent, that's when the plus c shows up. Plus c is the constant of integration. We have just done integration, so we have our constant of integration. A half plus 1 is 3/2. That's 1.5. So 2 times 1 is 2, plus 1 is 3. So this is x to the 3/2. And then 1 over 3/2 is 2/3. That's just us doing some arithmetic and algebra. There was one place where calculus happened when we went from the integral dx to the antiderivative plus c. How's everybody okay? Everybody looks super stoked. Finally, we're going back the other direction. We can take this derivative journey. We went forward, and now we have to go backward. So we're completing the story now. We go full circle. And then in 20 years, we'll do a reboot, get J.J. Abrams. And it's like, well, let's just do the same thing, but with more lens. Everybody gets mad at like the sequels, episodes 7, 8, and 9. So, oh, that's the same thing. It's like, well, do you not know how Star Wars works? Star Wars doesn't operate on story. It operates on nostalgia. No one cares about the story. Do you know what I mean? Yeah. So all the tricks that we did with derivatives are tricks that we're going to do with integrals. If I have an x, 1 over x to the third, we're going to read this as x to the -3. Then we're going to add 1 to the exponents and divide by the new exponent. Just like with derivatives, we have to be careful because our exponent is negative now. So we're going to have x to the -3 minus 1 over -3 minus 1. So it's going to be x to the -4 over -4. That looks terrible. We're going to write this as negative x to the, shit. This is all coming out terrible. Here are your options. Let's just put it this way. Here are your options. We got the coefficient is going to be a -1/4. If you write the coefficient -1/4, then you should write x to the -4. Here's one of your options. -1/4 x to the -4. If you don't like the negative exponent goes in the denominator. Only the x has a negative exponent. -1/4 does not have a negative exponent, so we don't flip that part over. So we could also write this as -1 over 4 x to the 4. At this point in our careers, we have switched over to, what's wrong? What did I do? We're supposed to add one to the exponent. I'll edit that out of the video. We all know I don't make mistakes. Because I was talking about derivatives right beforehand. So what do we got? What's negative? What are we supposed to do? Add one to the x. I was even looking at this when I wrote -1. Jeez. This is why I don't like when teachers are like, oh, my students aren't paying attention. Like, oh, motherfucker, you aren't even paying attention to yourself. You're going on autopilot. Why you be mad at them for being on autopilot? Thank you. That's 0 points for those, for 2 of you, minus 1,000 points for the rest of you. I'm just kidding. It's minus 1,000 points for me. Fortunately, I have infinite points. So I still have infinite points. Good. So one way to write this would be a -1/2 x to the -2 plus c. Write it coefficient times power of x. I like coefficient and power of x, especially when fractions are involved. I'm okay with negative exponents. This is a great thing to type. At this point in our careers, we're typing things with the equation editor when we're typing them on Canvas. So this is good. We don't have to worry about some single line syntax stuff. If you want to simplify the negative exponents, because you're like, oh, dude, negative exponents are just not acceptable. Then you can simplify the x to the -2. But make sure the x to the -2 drops down into the denominator and hangs out with the 2. The 1/2 coefficient does not have a negative exponent. It just has a negative sign, not a negative exponent. In single line syntax, this is just kind of awful. This is why we introduced the equation editor, so we could type our stuff. In single line syntax, my preference would be to write -1/2 x to the -2. Technically correct would be -1 divided by 2 x to the -2. Because we take the -1, divide it by 2, and then we multiply by x to the -2. There's nothing inherently that ties the 2 to the x to the -2. But most people will read the x with the 2. Most people attach the coefficients to the variable and not read the 1/2 power. So this is not great. It's technically correct, but if half the people are going to read it wrong, you can't write it that way. If half of your audience is going to read it wrong, you can't be writing it that way. So if you write -1 over 2x squared, that's the same problem. That's assuming that people will take the 2 and attach it to the x squared. You can't assume that people are going to read it in that way, because only half the people are going to read it that way. So if you want to make it clear, use parentheses. Now, there's no doubt. This is -1 divided by the product of 2 and the square of x. -1/2 can also, the negative can also hang out in the parentheses. It depends on how you're reading your fractions. Any questions? Comments? Snide remarks? How's everybody okay? We'll be typing these with equation editor. I know it's kind of a pain in the butt, but it's less of a pain in the butt than you taking a picture and uploading that. Because then I have to read your writing. And for some of you, if I'm looking at your writing and say you need to improve your penmanship, you need to improve your penmanship. Because I mean, like this. Any questions? Comments? Snide remarks? Is everybody ready for tomorrow? Product rule, quotient rule, chain rule. Do that, and you will crush the problems tomorrow. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. Oh,